pod to see more what questions are happening. Sure, ask about explicit time stepping in spontaneous or dynamic rupture modeling. So the question is, in situ stress, can you include an initial static calculation before time stepping? And do we use database initial stress to include initial stress throughout the whole domain? And how to handle remote stresses, and essentially applying loads for explicit time stepping. That's a good question. So if you're using a linear elastic material, then the initial stresses throughout the domain really don't matter. Really, when the spontaneous rupture modeling, all you really care about are the stresses on the fault surface if you're using a linear elastic material. So you don't have to solve a static problem. You can if you want, but generally you would solve that static problem completely separately, because that would involve using the PETSI solver, and you don't want inertia when you solve that static problem. You want the quasi-static formulation of PyLith, and you usually are going to want to put Dirichlet boundary conditions to solve that static problem. So in most cases, say for example you want to put on the lithostatic load, sort of like a rho GZ, you would calculate that for your domain using an analytical solution. Oftentimes I'll do a Python script for that to apply what my initial stresses are, create the spatial database, and use that as and apply that as a database for initial stress on my fault surface itself. To get the rupture started, there's a traction perturbation object which allows you to provide a complex time history if you would like to, for that initial traction to set the rupture propagating. For explicit time stepping, usually we put absorbing boundaries at the lateral edges of the domain and bottom, with no boundary condition on the top surface. And so that sort of, you can't have a Dirichlet boundary condition on the edges trying to create your tractions at the same time you have an absorbing boundary. The absorbing boundaries are essentially free surfaces when a wave is not impinging on the boundary. Another issue related to sort of when you would want initial stresses throughout the domain is if you're using the Drucker-Prager elastoplastic model, or if you were trying to use one of the viscoelastic models for a stress state to get some viscoelastic relaxation at the same time you're getting, with a sort of probably a very short time, Maxwell time, for viscous damping within your domain. Generally, we use either the purely elastic material or a Drucker-Prager rheology. And for the Drucker-Prager, you want that initial stresses associated with generally sort of the lithostatic pressure, although you could put in some initial shear in that as well. Any other questions? So there was a question about a dike intrusion and opening mode pressurization fracture and dynamic rupture. And since that's not using the PETSI solver, would we still need those modifications for fault friction? The answer is generally no. I have not tried a fault opening case as violent as a dike intrusion in a dynamic rupture simulation. When you open the faults, generally what it's going to want to do is it's going to want to make a free surface. There is a special setting to account if you still want those tractions applied to keep that fault open and not make it a free surface, then you still need that setting, which I believe is I don't remember the name of it, but it is in step 20, I think, .cfg. But in terms of the solver settings, no, those would no longer be necessary, but you may want to you probably still want to use the zero tolerance to make sure that then it's a matter of round-off errors when you're using the explicit time stepping in the trivial solver. Yes, open free surface equals false would be if you still want to apply the traction. Any other questions? Automatic time stepping and dynamic spontaneous rupture, generally no. Explicit time stepping is controlled by the CFL condition, and that is our current time stepping algorithm. We use the central difference scheme, and so the stable time step is uniform regardless of the deformation. And so you want to use something close to the what's given by the CFL condition. PyLith can output that for you. That is one of the values that's available for output. But generally, you need to set what that time step is for any of the explicit time stepping simulations, whether you use prescribed slip or spontaneous rupture, or bound or body forces, or any type of explicit time stepping simulation. Any other questions? Still have about 15 minutes left. There aren't any stupid questions. And if you have a question, someone else probably has the question too, so don't be afraid to ask questions. Have we done any real faults with PyLith? We have done um, a number of simulations with PyLith. Charles has done some subduction zone simulations. We've had people model all sorts of faults throughout the world with PyLith. Charles and I have done a project related to the Darfield 2010 earthquake, where we had non-planar geometry and 5 faults together rupturing with prescribed slip. So we've had people do quite a variety of simulations with PyLith. If you look on the CIG website, you can look and see what papers have been published with PyLith. And you can also see other simulations done with and the dynamic rupture benchmarks. I wouldn't call them real faults, but they are starting to get more complicated with a variety of initial conditions. Almost all of them are artificial in some sense. But there has been a number of real papers on quite a variety of science done with using PyLith. So we have a question between implicit and explicit. Dynamic rupture in only a very small part of the whole time duration, and most of it should be quasi-static. How do you suggest to handle it? Well, I would do quasi-static for all the deformation up until the point that you need the dynamic, so that you use the sort of initial conditions. I think what you're getting at is you need the initial conditions for your spontaneous rupture from your quasi-static simulation. So like your initial stresses on your fault from a quasi-static simulation applied to a dynamic simulation. And that's, we've actually set up, I believe, 2D subduction step 4 takes output from a quasi-static I believe, from one simulation, uses it to drive after slip in a viscoelastic relaxation. Sorry, not viscoelastic relaxation, static friction problem. So the best case is when you do have the 2 different time scales is to use your quasi-static for your long time durations. Otherwise, if you try to do explicit with all those short time steps, it would take forever. We are working on migrating towards earthquake cycle modeling where we can flip back and forth between the two. So when you have your deformation is occurring fast enough and inertia is important, it would automatically switch. There's a number of steps leading up to that, with the next step being switching to the PETSI time stepping algorithms that allow us to give us more flexibility in terms of the time stepping algorithms and really true adaptive time stepping on the implicit simulation. So you can take bigger jumps when the deformation is small. Right now, for the viscoelastic deformation, we assume that you just need 10 time steps per Maxwell time. But if your deformation is occurring very slowly, the solution would be stable even if you took bigger time steps. Any other questions on this session or any of the previous sessions? Yeah, we're working on the gravity. We think things are working fine for infinitesimal strain. Looks like we still have a bug in the finite strain. When we add in the gravity, we need the gravity vector to account for the deformation. So we still have a bug to fix, and we then want to create good examples that show how to use gravitational body forces and initial stresses in a real example. So we're probably looking at, given our schedules of doing that, sort of probably mid to late September after the SCEC meeting. For those everyone going to SCEC, we hope to be sort of finishing things up by then. So we will look at our various schedules and come up with a time for that tutorial. It'll probably be either a 1 hour or 2 hour tutorial, we don't know, but we'll pick a time. If we have a couple time slots, we can always do a doodle poll and send that out to the CIG short and let people vote on when they want the tutorial. Generally, I think it would probably be at one of these two, probably the later afternoon US, afternoon/evening for people within the US. That allows Charles to join in the morning in New Zealand. So yeah, we'll get the slides up from the debugging session. We're done here. And we'll also be sending out a post-workshop survey. This was our first online tutorial. We went back-to-back days and only 4 sessions. Previous incarnations were spread over Monday, Wednesday, Friday of 2 sessions. We're also doing 2 time zones, 2 schedules for accommodate a wide variety of time zones. That was extremely laborious in terms of the number of sessions, so we really didn't feel like we had time for that this year, so we cut it back. And so we'll try and get your feedback on how well this worked compared to what's worked in the past. Trimming down to 4 sessions. Obviously, we can't cover quite as much, but we also have the videos from previous years online. So we're trying to find the balance between making stuff available and not covering the same material every time, but then also not making it too much of a time burden on for people being able to attend and accommodating all the variety of time zones around the world. So final call for questions. Does any part of PyLith cover induced seismicity? Generally, I would say no, there's nothing explicit in PyLith for induced seismicity. If you really trying to think about pore elasticity and fluid flow, then some of the features in our multi-physics implementation, which is one of the things we're working on, would prove helpful. But in terms of sort of growing fractures and those type of things, it's not, we generally assume we know where the faults are beforehand, but certainly fluid flow is something that we are planning to include and coupling that to the elasticity formulation. So it'll probably be much more relevant in the future once we have the multi-physics implemented. So thanks everyone for participating, and I guess we'll see you online. And if you see us at the AGU meeting or some other conference, please introduce yourselves. It's always nice to put a face to people